Okay, it's recording. Let me share the slide. Sorry. This one. Yes. Okay. So far we have talked about how I talked about ISA instruction set architecture. Basically, this is a way how we are writing some instructions and through which we are talking to the computer. How whatever I have written in the software instruction part, how they are getting mapped to the backend hardware where our actual instruction is execution is taking place. So do you have any question regarding yesterday's discussion? No? Anyone? Okay. Then here are a few types of embedded processors that we generally use. One you already know, you're very familiar with it.
Ma'am, are you presenting? Your screen is not visible if you are presenting, if you are using slides.
Yes? Pardon?
Ma'am, are you using slides?
Yes, you can't you see the slides?
No, no.
No?
No, ma'am, slides are not visible.
Wait, I have already shared. Wait, screen share. It's there. Okay, now can you see the slides?
Yes, ma'am.
Okay.
Yes.
Okay. So far we have talked about that ISA and those parts. Now you have the idea, I hope, that in whatever platform I'm using, whatever processor I'm choosing, maybe it's a microcontroller, maybe it's a VLIW, in some way or other, wherever I'm writing some instruction, how they are getting mapped to the backend hardware. Okay. So we know that there are different kinds of embedded processors. One is very common to you. First one is a microcontroller, which is a small computer on a single integrated circuit, and which consists of CPU. Of course, that is simpler CPU compared to general purpose heavyweight computers. And associated with it, we have memories, I/O, and timers. So simplest microcontrollers, sometimes we use in our lab for experimental setup also. Those are 8-bit words. And since they are small in every aspect, we understand that they consume small amount of energy. So they are used in this type of sensor networks, nodes, surveillance systems, where small amount of energy related applications are developed. Now this is quite common thing. Few important information is that some processors, what we generally think, they are generally for desktop, like x86 family, those CPUs. They are still nowadays they are also getting used in netbooks and small mobile computers. So they are basically the member of this 86 families, and that way they are also sufficiently equipped to handle, to work within lesser amount of energy. But there is not much degradation in terms of performance. So these type of processors, you can think sometimes based on their instruction set architecture directly, maybe sometimes you can think they can have general purpose. But sometimes when you are thinking in terms of lesser energy requirement and all those features, you can think they are more in the side of microcontrollers. So they are generally, we can consider they are in the boundary. They can consider as a boundary between general purpose computing and microcontrollers. Another typical application specific processor that we generally mention in this embedded processing domain, that is DSP processor. Now, in our introductory discussion, we mentioned it at application specific processor, and we mentioned that okay, these are basically typically used for specific application domains. Now, here in this coming 2-3 slides, we will discuss few properties of these DSP processors, that why they are suitable for these type of applications. These are few, characteristics of a DSP processor: a hardware multiply accumulator unit, several variants, and the three important things are circular buffers, auto increment in the addressing mode, and typical special type of bit reverse addressing. So we will just mention a few about these comments. Okay, these top points. First one, I think that much that these are used in single signal processing applications where we need some sophisticated mathematical operations to be performed on input stream of data. Those are like filtering, those are like frequency analysis, those things. Okay. Now, due to the nature of this requirement, we add few typical features there. Those are only present in this DSP processor. One is that among them, one is circular buffer. What does it mean? See, whenever we are in general purpose processing, we are trying to perform these type of operations. You can see this is AI. You are summing over AI into xn minus y. Okay, that means each time you are taking this value and so on, right? Now for this, what do you need to have? Gradually you will store this xn minus values, xn minus 2 and so on. If you do this, and once you are already processing this a0xn and a1 xn minus 1 together and you are getting the summation result, of course there is no need to store this xn separately, right? But if you want to do in a general array type of structure, what we have in our general purpose processing, there if you do this, you will just allocate some array, you will add there continuously, and at a certain point of time, these value, with the increase of this n, this array size will increase. Okay, so if depending on the value of this n, you have to decide your array size. But with the use of circular buffer, what is the advantage? That you are maybe deciding, you are maybe choosing a typical buffer, this circular buffer, where you are maybe allowing these 8 locations, 0 to 7. Okay. When this 8 location is filled, the next xn minus ith element, you are again storing back to this 0th location. Then 0th, 1th, specifically, basically you are overwriting all this subsequent locations repeated. In a repetitive manner. So what is the advantage? Of course, you can understand that you are saving in your application, you are saving the required array size. You are saving in terms of memory size. So this is one advantage or one typical added feature that DSP processors use, because in those processors we repeatedly use these type of operations, repeated multiplication and additions, and of course if you override these values after some particular times, particular delay, then there is no harm in it. So this is one typical feature of DSP processor. Another typical feature is automatically incrementing. So whenever you are having a register, in the next given or next input, that register location, whatever memory value it is holding, it is basically increasing to the next memory location. So auto increment fetch. Another one is bit reverse addressing. What does it mean? This is mainly required for FFT algorithms that we heavily use FFT multiplication, FFT related domain operations, mathematical operations. We heavily use in this signal processing domain. And when we do that, sometimes we have to access values like x1, x2, x4, and so on. Okay, when we create that butterfly part. In different layers, I'm not going to that into that algorithm, but the main idea is, in this case, if you just follow the typical addressing like x1, x2, x3, x4, that way once you auto increment or increment your addressing location addressing field, that will give just your next sequence of address, that will not suffice. So for that, a typical addressing technique is used, that is called bit reverse addressing, where you manipulate the bits in such a way, addressing bits in such a way, that your next location immediately give you the next required value. Okay, for that is required for FFT algorithms. So these are the few features those are used in DSP processors. And for that reason, we call it, this is a typical application specific, because these bit reverse type of addressing or these type of requirement of circular buffers may not be, I mean, these features may not be heavily used when we are thinking of general purpose processing. Okay. So similarly, of course, x86, we know that these are dominant in general purpose desktop and computers. But of course, I am not going to the details of it, but if you are interested, after there is serious improvement or in power handling, you can go to this reference where you can find some examples and some improvements also related to x86, which shows why x86 is also an attractive option nowadays for embedded application or embedded computing. Okay. So we see we have these type of different, processing options. Another one is graphics processing. In graphics processing, the main important idea is it supports huge parallelism. Okay, where you can support the different hierarchy in terms of memory. We will talk about this type of hierarchy, memory hierarchies later, maybe in the next class. And also along with that, it supports different thread libraries. So these are different options you have. But the important part is that we have to understand, in spite of that, we have developed one thread library, and my compiler is supporting and doing different, giving some idea how we can use those threads efficiently. But ultimately, it is underlying the hardware that should support this thread running requirements. That should support this parallel execution. So how we are actually supporting this parallel execution in the hardware level? I mean, starting from our software instruction level to the hardware level. So this is just one basic idea. When we mean concurrency, this is conceptually executing the different parts of the program simultaneously. Parallelism means you are actually physically executing this. So we will see what modifications we will be doing in the hardware to physically execute different parts of our program in parallel. Now, when you are writing a program, what the compiler does, the compiler, whenever it compiles, it also does another thing. It does some data flow analysis. Remember, we have also talked about this data flow analysis, and where we have mentioned how in this, I mean, whatever operations and whatever data flow are there in your sequence of instructions or sequence of programs, how you can arrange them. And in case of parallelism, compiler adds one extra step to check that how much parallelism compiler can allow in their instruction execution part. Now, the simple idea. you are having, your compiler wants to do two additions maybe, or two multiplications. Maybe you can take multiplications are costly. So these are two inputs and these are two inputs here. So your compiler wants to do two multiplications in parallel. But how is it possible if your hardware is not supporting that? That means some way or other you have to apply this concept of parallelism, or perform something, some change in your hardware so that this parallelism can be handled in a proper way by your hardware. Okay. So we will come into this. We will talk about different type of processes where this parallelism is best supported. That is multi-issue instruction streams, VLIW. We will come into this. Before that, one important concept. See, why it is critical in case of in general purpose processing also, when we are thinking about parallelism, our main goal is to improve the performance. Like you are trying to execute a program, your motive will be, I want to do as fast as possible. Okay. But when we are thinking in embedded system, embedded systems they are mostly real-time requirement with real-time requirement. That means, of course, you have to meet some deadline. This is the first thing. The second thing is that it is not that you have to only do as fast as possible. You have to be just in time. Think about one plant. Okay, when your feedback is coming, there is a sensor, there is our initial example of our cyber physical system, where your plant is expecting some feedback, or you are getting some input from the sensor. Now everything must have to be just in time. It is not that you have improved your performance in a huge way, and your whatever input is you are expecting at some, just say at some x1 second, at the x1 tick of your clock, you are getting it much before that. Then that input also not very much useful in your embedded system scenario. This is not the case of general purpose computing, because general purpose computing means if you have supported huge performance improvement, and your general purpose processing is getting finished, your program is getting finished much ahead of time, that is pretty good. But in embedded system, too much before and after, both are deadly. So you have to be just in time. For this reason, whatever performance improvement you are suggesting or you are giving, that must be also calculated. Okay, this is one basic difference when we are talking about general purpose processing and embedded system processing. Okay. Now we will discuss today mainly this part, how we are actually applying parallelism in hardware. And the main general concept is, first and foremost concept is pipelining. Before going to the pipelining part, let's start from our previous discussion, what we have discussed yesterday. When we have talked about instruction set architecture, what we discussed, that we have written some instruction. That instruction we have compiled. Our compiler has generated some code. That code, when it is getting calculated to the hardware level, we are storing that code to some memory. Okay. After that, there is a step of instruction fetch, where we are taking fetching the instruction. Then we are instruction decode, instruction fetch, then instruction decode. Decode means we are checking what does this instruction mean. Is it a jumping instruction? Is it an addition instruction? Subtraction instruction? And what does it mean actually? Once we decode it, after that, we do the execution. That means based on that, we send our data and control values to our subsequent ALU units. Okay. From there, we come to this memory access part. That means if now I have to store this value in some memory, then I will do this part. Write back. Write back means write back to some register. If whatever value we have generated, that I have to store back to my register file. So these are the 5 main steps in the instruction execution. Now we will see what these are how these components help us to achieve these stages. Then we will see what is the pipelining. See, now here, whenever our instruction execution starts, this is our PC, okay, program counter. So program counter fetches some instruction from a memory. Okay, let's take one example, then we will see different parts of it. So let's say this is our first example. This is simple addition. Maybe your opcode is giving some addition, operation, subtraction, whatever it may be. But for that, you have some 10 values, 1010 values in this 32 formats. It is 32-bit. So in this few 32-bit values you have. So what PC is doing, if it is your instruction memory, basically both way it is written memory and memory. This is for instruction and this is for data memory. Okay. PC is fetching instruction from this memory, and I will come this part later. First you understand this part. From this part, it is sending the value to the instruction register. That means your instruction register is holding now what current value you have to execute, what current instruction you have to execute. Okay. Now within this instruction, you have these fields. See, from there, this RS-RT, you can think about this RS1 and RS2. These are coming to this register files. Okay. Now from this register file, these value goes to these 2 marks. I will come later why there is a marks. Just think now, as of now, somehow it is going to the input of this ALU. Okay. From this ALU, this is the output of the ALU. Now this ALU, there are 2 options based on your instruction. Maybe this can go to this memory. You can store directly to this memory. But here in our case, it should get stored in this some register value, right? So from there, some register value, that is, it may happen that is holding the value of the memory. That is a separate case. Here we are thinking that it is just getting stored in that register value. So here, see, there are 2 inputs. The same ALU output is either going to this memory or it is going to this part. Okay. So this part, again, I will come why this marks is there. This part is again going back from here. You can, I hope you can see, it is going back to the register file. That means these value, this is a write back. It is getting stored in our register file. So this way, with these individual components, you can see how these individual components are helping us to actually execute our requirement. Now, what is the idea of pipelining? Idea means you are whenever you are fetching the single instruction, you are just going step by step. Instruction fetch, decode, execute, mem, and write back. And once you are finished with up to this write back, portion, then only you are executing your next instruction, or you are starting with your next instruction. But in case of pipelining, what you are doing, it is something like this. You can see instruction fetch, instruction decode, execute, and so on. Next, immediately when your instruction, one instruction is going from this instruction fetch to instruction decode part, you are starting your instruction fetch part, because at that point your DS module is free. So at that point you are again starting your instruction fetch operation. That way you are basically making it parallel. You are parallelly executing this instruction decode and instruction fetch. Okay, so this is the concept of applying parallelism through pipelining. Okay, is there any question? First of all, just for this part, we will again come back to this diagram again and again with some different types of instructions.
Ma'am,
Yes.
from the ALU, like it is also coming back to the PC part. It is connected in the upper marks, and then it is getting
Upper marks. I will come to the upper marks. That is for branching. This one you are telling, right? This part. Sorry.
Yes, ma'am.
You are telling this part, right? This marks. Hello?
Yes, ma'am. Yes, ma'am.
Yes. I will come into that. I am just talking about this register type of instruction, how it is getting executed. This one is for, okay, since you asked, let me go there. This is for branching type of operations. That means it may happen your instructions is like this. You have considered some maybe branch if equal, then you have given this is the opcode for branching, and you are checking that this RS and RT, if they are equal, then you will jump to some immediate location. Or maybe this is not some immediate location, you may be specifying some typical memory address location. Okay, so for that reason, for that case, what will be the flow? Of course, see, for that, in that case, you are actually fetching that instruction. You are coming here and you are taking this value as if it is 0 or not. Okay, for that, wherever you have stored this this is for binary, branch if equal. This component is for branch if 0. That means you are storing a particular, you are checking one particular register value. See, once you have done this instruction fetch, from there this register file is giving you some value of this register. This is coming here, and this is again going to this 0 is 0 checking module. This module checks if the given value from this register file is 0 or not. Okay, if it is 0, it sets a 1 bit to this branch taken value. Okay, now you see this branch taken output is working as a selection of this marks, right? So now in this marks there are two inputs. One is general input. See, when we do general execution, I have written defined add this, subtract this, multiply this one by one. So what my PC does, program counter, it immediately goes to the next instruction. How it goes? See, here this is the program counter. With that program counter, there is an adder. So one input of PC goes to this adder, and another input takes the value of +4, generally +4 in this case. That actually, if I go for the memory structure of it, that is the location of our next address. So this PC, first let's consider as of now some offset value plus based on how you have designed your memory. It may be anything. So based on whatever offset you have given, PC plus this offset value gives the immediate next sequence address, immediate next instruction address in your instruction memory. That means if there is no branching, there is no concept of branching, there is no concept of jumping. then you will just go to the next instruction. So this is the next instruction coming to this mux. Okay. Otherwise, if there is a concept of branching, you have maybe given some register file input. From there you have calculated some offset, and based on that you have computed if there is some branching, if there is some branch, if 0 satisfied, where your PC will jump. So that input is coming from your ALU output, right? So this one is one your ALU output is giving if branch is taken where your PC will jump, and if there is no concept of branching, that means if this E0 condition is not getting satisfied, then your PC will jump into the just immediate next instruction. See, this is coming out from this adder from here. So these are the two inputs in this mux, and based on this selection line, the selection says yes, that register value is 0. So if it is 1, take the jump. That means now you see your PC is getting updated. This is your PC value, next PC value is getting updated based on this condition. Okay. Mainly this part only decides your program counter will fetch which instruction next. Clear?
Yes, sir.
Okay. Everybody? Wait. Yes. Yeah. Okay, fine. So this is the requirement of this. Of that part of mask. Now let's check. So our type of instruction we have discussed. We have discussed jump type of branching discussions. This is for immediate. Okay. See, for immediate, you remember that you have given some immediate value. Maybe that is maybe some 40 or 50 something. That 50 will fetch from this address part, and then you will be adding, subtracting, whatever it may be based on whatever opcode you have given, and then you will store that to this address. Now you see, when your instruction register is fetching that type of address, one input is coming from this register file. Okay, and the another input is coming from this immediate part, that is whatever you are getting in this instruction register. So that instruction register, actually you cannot directly take it. There is a one concept of sign extension, and after that you are taking these two values as an input to this ALU, as inputs to this ALU. Okay, so that's why you are having two mux here. See, mux 1 and mux 2, where you are actually having, because there are two possibilities. Sometimes you have to fetch the input from the register file for your ALU. Sometimes you have to consider inputs from your immediate part of your instruction register. That is not coming from any register. That is direct immediate value that's set in your instruction. So that's why these marks is given here. And for these marks, okay, sometimes you have to compute that direct values from your register. Sometimes that PC value will come and then you have to compute with some offset. So for that purpose also, the same ALU you will be using. So whatever possible, according to your instruction set, whatever possible usage you are making from your ALU, because your ALU is one. Whenever you want to do some addition or multiplication, you have to use that same ALU. Maybe for addition, that addition is directly coming, that addition requirement is directly coming from your instruction request. Maybe it is coming to update your program counter to understand, okay, where I will go next. Maybe sometimes that address request, ALU usage request is coming from types of branching you are handling. So whatever may be the case, in any case, this type of what to say, the same ALU you are using. That's why there are different provisions to select which input you will check when. Now see, here we are just showing the data path, mind it. See, we have not, except for these marks, we have not shown any selection line for any of the marks. And also we have not shown, see, I am telling that when, maybe I can go back to these example ones. I am telling that this addition, whatever I have done, I will store it back to this register file. But register file is also huge. So of which location, in which location, for which word I will modify in this register file or in this data memory to update the value. Those parts are not shown here. This is only the data path part. The control part, it's not shown here, but you can understand that control part is also coming for this opcode part. Depending on the opcode part, there are some inputs also to this selections of this each and every component. Okay, so this is the basic idea of how we are actually computing this branching, different type of instruction, maybe register type, immediate type, branching type. You can think of jumping. Jumping is quite simple because we are just selecting the opcode, we are jumping to that target. Okay, this is just using this part, upper part. So that way, how these type of instructions, whatever I have stored in my instruction memory, this is my instruction memory in the form of 1 and 0. We are just setting this 1 and 0 as a control inputs and some as data input values, and how this instruction we are processing using our hardware. Okay. Now, when we are talking about pipelining means that these are my 5 stages. Okay, and for each of the instructions I am using, or you can actually think about these type of diagrams, that will be easier for you. You are doing instruction fetch, then you are doing instruction decode, execute, then mem part, then memory part, then register write back. Okay, then again for the next instruction you are starting the fetch from here, then you are doing the decode, then you are doing the execute, and so on. For next instruction you are starting the fetch from here, and so on. Okay, so based in this way you can see, when you have the without any pipeline, when for us to maybe when you are executing 5 instructions, maybe 2 instructions, at that time for 2, 5, 10 clock cycles would have been required, because considering that, okay, you are in 1 clock cycle, you are actually completing 1 stage, maybe that is fetch part, decode part, whatever it may be. But when you are using this type of concept of pipelining, just you can finish those 2 instructions in 6 stages, or 6 cycles. So there is for these 2 instructions, you can see you are actually saving few clock cycles. So this is the basic advantage of pipelining, and for that the main intermediate part we use these registers. These are the registers. Maybe when we are just using directly without any concept of pipeline, some registers we may not use. We can directly send the value to this next level of inputs, next level of components. But to implement these pipelining strategy, implement these to give the support of this parallelism, we are actually using these intermediate registers. Those are typically pipeline related registers that we use to send input to the next levels. Okay, but things are not so simple. Okay, do you have any question up to this? Should I repeat any part? or everything is clear?
Ma'am, could you repeat the pipelining part? I could not
Okay.
understand.
Okay, you couldn't understand, right? So can you repeat with me? Let's say I'm going to do which type of instruction? Do you want this immediate or this type of instruction?
Ma'am, when you were telling about we completed 2 tasks in lesser time. On
Okay,
that.
when you are completing two, see, these are the stage by stage execution, right? So maybe this is for the instruction 1. Okay, for first instruction, you are okay. Maybe I can open one notepad and I can write. Can I write it? I don't know whether I can write it. Okay, I can. Wait.
Ma'am, you were explaining about on the last slide.
This part. Okay. See, here you can see this is stages. Okay. Maybe you can think about this. These are the stages. Stages means you are having instruction fetch, instruction decode. Those are your stages.
Yes, ma'am.
So you can see these are the stages. These are the stages given. Now when you are in stage 1, okay, if there was no pipeline, think about it. If there is no pipeline, what you used to do? You used to do for your instruction 1, these are the number of instructions. I don't know what is happening. These are the maybe number of instructions. So for first instruction, I will have this instruction fetch, right?
Yes, ma'am.
Then instruction decode. Then you will do the execute, right? Then I will do this what to say, memory, right?
Yes,
Then
ma'am.
I will do the register write back. Okay, these are the 5 stages.
Yes, ma'am. This is for one complete task.
This is for one instruction, single instruction.
Yes,
Okay,
ma'am.
for each instruction we have to do this 5 stages. We have to do this 5 stages.
Yes, ma'am.
So initially, when there was no pipeline, the disadvantage was that we have to wait till this 5th part, stage 5. Then only we can start from one instruction again. I mean, that time your next instruction, you were starting from this part.
Yes, ma'am.
Instruction page, again decode, again execute, and so on. So effectively, you are using 10 clock cycles.
Yes, ma'am.
Is it clear? Without pipeline. But now we are starting this instruction phase. Instead of waiting all the stages to getting completed, we are starting from here. Okay. Now you are starting your next second instruction, because at that time, since you have already used, go back to this diagram, you have already used this intermediate register, and you have already fetched whatever values you need to be stored in this register. So for next level, whatever processing it is will be there, these registers can act as the source of input. Okay. Then your
So,
memory
ma'am,
is
the first task, if the first task is in the ID register, then in the first task, the second task has already begun and it probably has reached the IF. So
exactly.
if
The next task already whenever the first task in ID, the second task is already in the IF stage. So whenever the first task is finishing this ID and it is going to execute, second task is going from instruction page to instruction decode.
Got it.
Right? Now in this way you calculate, it will be at most 5 stages, and so 2 plus 1 6 clock cycles.
Yes, ma'am.
Where initially maybe there was a requirement of 10 clock cycles. So here for 2 instructions you were saving. That way you are executing huge number of instructions. So expected that you will save huge number of clock cycles. Clear?
Thank you.
Okay. So that's all. I will not start the things are not so simple. Okay. So next step we will see that in spite of the fact pipeline is giving some amount of advantages, but whatever advantage I will get, it's absolutely based on what type of application or what type of program I'm running. What are the intermediate data dependency, also control dependency I have? For example, okay, examples I will take next. Some value, maybe you are sequentially trying to execute two instructions. One is adding two values and you are storing them to maybe register 5, and in the next instruction you are fetching some values from register 5 and you are applying on them some another operation, maybe some subtraction from that register. Now see, if you are directly blindly applying pipelining to them, so what will happen? This instruction fetch, after that you are doing the instruction decode, execution, and then register write back. Basically, in this stage, in this final stage, your register 5 is getting updated. Okay. But when you are starting your next sequence and you have fed that next instruction to your pipeline, you are doing this instruction fetch, instruction decode, and here you are doing this execution part. The execution means you are maybe doing some subtraction from the value whatever stored in your register 5. But now think, in this stage, your register 5 is still not updated with your previous computation, because your previous computation still now not reached till this register write back part. Register write back stage. So whatever data you are using in this second instruction is maybe some earlier data or some junk data. So these are typical few incidents, typical few scenarios we will discuss next day, because now we do not have any time. Next day, these are called pipeline hazards. So there are two types of control. One is a control hazard, and this whatever example I have given, that is called data hazard. So what are the typical hazards you can face in pipeline and how you can actually overcome? Okay. So this part we will talk about, and then we will move to our software again development discussion. Okay. Clear? Any question from this part? What you do whenever you go through this pipeline part, just draw this diagram and step by step go through these instructions. Then things will get clear. Okay. Any question?
Not yet, but we'll go through that.
Yes, go through them and consider each of the instructions separately. Do not march everything. Sit with the diagram and then think how actually you are going to execute one single example instruction through this pipeline hardware. Okay.
Okay, ma'am.
So that's all for today's discussion. Next day, tomorrow I will talk about this pipeline hazard a bit. Then I will move to the software. I will start the discussion on the typical software design part. That's all from my part. Thank you.
Thank you, ma'am.
Thank you, ma'am.